Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
Great to be back.
Today, we are diving straight into, well, the really core stuff.
Yeah.
The foundational mathematics that underpins thermal and fluid dynamics.
That's right. Vector calculus and conservation laws.
Yeah, and one of our listeners shared some sources, and they highlighted something we see a lot, don't we? Textbooks, papers. They often jump straight from these core differential equations like, boom, into really complex applications.
Oh, yeah. Things like thermal spreading analysis or optimizing flow channels.
Exactly. And there's this gap, this canyon almost, between the pure math and the practical problem.
It really is. You can't fully appreciate the solutions, the clever designs, if you don't speak the language the problem is written in,
Absolutely. So our mission today is to try and bridge that gap, connect these abstract mathematical tools, your gradients, your divergences, to things we can actually measure and design around, like heat flow paths or how stable the fluid flow is.
Precisely. We need to get comfortable with the physics of fields before we can really manage the fluxes, the energy transfer, the momentum transfer. It's about understanding that language first.
Okay, so let's unpack this a bit. When we're analyzing heat transfer or fluid flow, we're fundamentally dealing with fields.
That's the key concept, fields.
Like temperature, that's a scalar field, right?
Yeah.
Just has a magnitude at every point.
Yeah, just a number. How hot is it here?
But velocity, that's different. It's a vector field. It has magnitude and direction everywhere.
How fast and which way the fluid's moving at that point.
So to describe how these fields change across space, we need these tools, these vector operators.
Exactly. And maybe the most intuitive one to start with is the gradient, usually written as nabla T for temperature.
The gradient of temperature. Conceptually, what's it telling us?
It's giving you two key pieces of information. One, the direction of the steepest change in temperature. Think of it like the steepest uphill direction on a temperature map. And two, the rate of that change. How steep is that hill? So if you put a hot chip on a cold heat sink, the gradient vector points directly along the fastest path heat wants to take.
Right. And in simple rectangular coordinates,
Right.
Your basic X, Y, Z system, the formula looks pretty clean.
It does. The gradient of T is just, well, it's a vector sum. You take the partial derivative of T with respect to X times the X unit vector, plus the partial of T with respect to Y times the Y unit vector, plus the partial of T with respect to Z times the Z unit vector.
Equation 1.31 in the source. Straightforward enough.
But, and this is a big but, the math changes quite a bit depending on your coordinate system.
Ah, right. Cylindrical or spherical coordinates. Always tricky.
Exactly. Imagine analyzing flow in a pipe or heat spreading from a cylindrical heater. You switch to cylindrical coordinates, or theta Z,
Okay.
and suddenly that gradient formula gets more complex. Specifically, look at the angular component, how temperature changes as you move around the cylinder, the theta direction.
What happens there?
You get this extra factor. It's E sub theta times 1 over R times partial T partial theta. See equation 1.36.
So the radius matters directly in the gradient calculation.
Immensely. That 1 over R term tells you that the same angular change in temperature contributes less to the overall gradient if you're far away from the center, large R, because it's spread over a wider arc.
Ah, okay. So close to the center, a small angular change looks steep. Far away, it's shallower.
Precisely. Geometry dictates the math. It's not just a change of variables, it changes the structure of the operator.
Okay, so that's the gradient, focused on slope and direction of change. What about the other big operators for fields, especially vector fields like velocity?
Well, we absolutely need to talk about divergence, nabla dot V, and curl nabla cross.
Divergence. What's the physical intuition there?
Think of divergence of velocity as measuring expansion or contraction. If you draw a small imaginary box in the fluid, is more fluid flowing out of the box than flowing in. If the divergence is positive, the fluid is expanding, like it's coming from a source within the box. If it's negative, it's contracting, heading towards a sink.
Yeah.
If it's zero, well, we'll get to that. It's crucial for mass conservation.
Got it. Source or sink. And curl, nabla cross V.
Curl measures rotation, local rotation, or vorticity. Imagine placing a tiny, tiny paddle wheel in the flow.
Okay.
Would it spin? The curl vector tells you the axis it would spin around and how fast. If the curl is zero everywhere, the flow is called irrotational.
Which I assume makes the math easier.
And it's significantly easier in many cases, yeah.
And sometimes these operators get combined, right?
Yeah.
I see the Laplacian mentioned, Nablus squared T.
Yes, the Laplacian is basically the divergence of the gradient. So for temperature, Nablus squared T involves second derivatives like partial squared T, partial x squared, plus partial squared T, partial y squared, and so on. Equation 1.35 shows the rectangular form.
And that's important because...
Right. Because setting the Laplacian of temperature equal to 0, nebula $2 and vor, describes steady-state heat conduction with no internal heat generation. It's often the starting point for solving basic heat transfer problems in solids.
All right, so we have this mathematical language.
Yeah.
Gradient, divergence, curl, Laplacian. Now, let's apply it to the fundamental rules governing how things, especially fluids, move, conservation laws.
Starting with the big one, conservation of mass. This gives us the continuity equation.
Okay.
In its most general form, for a compressible fluid, the equation looks like this. Partial rho partial T plus partial with respect to x of rho v sub x plus partial with respect to y of rho v sub y plus partial with respect to z of rho v sub z equals 0. That's equation 1.58.
Whoa, okay, break that down. Partial rho, partial T.
That's the rate of change of density, rho, over time at a fixed point. It's how much mass is accumulating or depleting in a tiny volume.
Got it. And the other terms?
Those are the divergence terms, essentially. They represent the net rate at which mass is flowing out of that tiny volume in each direction, x, y, z.
So accumulation rate plus net outflow rate equals 0. Mass isn't created or destroyed in that volume.
Exactly. It's just a mathematical statement of mass conservation.
But you mentioned compressible flow. What happens if the fluid is incompressible, like water or oil, where the density rho is basically constant?
Ah, that's where the magic happens. If rho is constant, its derivatives are 0. So that first term, partial rho partial T, vanishes.
Okay.
And you can pull the constant rho out of the other derivatives. Since rho isn't 0, you can divide the whole equation by it. What you're left with is beautiful.
Which is?
Partial v sub x partial x plus partial v sub y partial y plus partial v sub z partial z equals 0. See equation 1.61?
Wait, that's just...
The divergence of the velocity vector, nabla VO not VA equals 0.
Wow, so for incompressible flow, the velocity field has 0 divergence everywhere.
Exactly. It mathematically states that the fluid isn't expanding or contracting locally. What flows in must flow out. It's incredibly elegant and simplifies fluid dynamics immensely.
Okay, that's a huge insight. Now, when we're tracking fluids, there's this other concept mentioned, the substantial derivative, or material derivative. Why do we need that?
Right. The substantial derivative, often written as capital D by capital DT, we need it because usually we don't care just about how things change at a fixed point in space. That's the partial derivative with respect to time, partial T.
We care about what happens to a specific chunk of fluid as it moves along.
Precisely. We want to know the rate of change experienced by a fluid particle as it follows its path. Think about tracking a floating particle and measuring its temperature change.
Okay, so how does the substantial derivative capture that?
It combines two effects. Look at equation 1.55 for density. dRO by dt equals partial rho partial T. That's the local change at a point.
Right.
Plus v sub x times partial rho partial x plus v sub y times partial rho partial y plus v sub z times partial rho partial z.
So those extra terms involve the velocity, v sub x, v sub y, v sub z, and the spatial gradients, partial rho, partial x, etc.
Exactly. That second group of terms is the convective derivative. It accounts for the change the particle experiences simply because it's moving to a new location where the density or temperature or whatever property is different.
Ah, I see. So ddt, local change, plus convective change. It follows the particle.
You got it. It's essential for applying Newton's laws to fluids correctly.
Which brings us to conservation of momentum, the next big conservation law.
Yep. This is basically Newton's second law, Favre, applied to a fluid element or a control volume.
The source is stated as a theorem. The net force F on a control volume equals the time rate of increase of momentum inside plus the net rate at which momentum flows out across the surface, equation 1.66.
That's the integral form, yeah. It accounts for all the forces, pressure pushing on the surfaces, viscous shear stresses acting like friction, and body forces like gravity.
And when you take that principle, apply it using the substantial derivative, and specialize it for, say, incompressible laminar flow with constant viscosity.
You end up with a set of complex, nonlinear partial differential equations. The famous, or maybe infamous, Navier-Stokes equations, like equations 1.69 and 1.70, shown for cylindrical coordinates.
They look incredibly complicated, especially in cylindrical or spherical coordinates.
They are, but the core idea, the engineering insight, is that they are fundamentally just $5 for a fluid. They balance inertia, pressure gradients, viscous forces, and external forces to determine the fluid's acceleration and therefore its velocity field. They describe how pretty much every liquid and most gases move.
Okay, wow. So we've built up the language and the fundamental laws. Let's shift gears now and connect this back to more tangible, practical things a designer actually grapples with, starting with heat generation inside a solid.
Good idea. Let's take a simple case. A slim conductor, maybe a wire or flat plate, with heat being generated uniformly throughout its volume. Maybe it's resistive heating, $2.
Okay, uniform volumetric heat generation. And let's say both ends or surfaces are kept cool at a constant temperature, sub-zero.
Right. So heat is generated everywhere inside, and it has to flow out to the cooler boundaries. Where will it be hottest?
Intuitively, right in the middle, farthest from the cool edges.
Exactly. And there's a simple formula for that peak temperature, Tmax. It's Tmax to the 0 plus the Qg Fricke L2. That's equation 1.4. Here, L is the thickness, or total length, and K is the thermal conductivity.
Tmax equals T0 plus Q sub G times L squared over 8K.
Okay. Now, here's a really useful practical insight buried in that equation, highlighted as equation 1.5 in the source material. Compare this case distributed generation to a case where the same total amount of heat is generated, but all at a single point or plane right in the center.
Okay.
The thermal resistance for this distributed case, where heat is generated everywhere, is only 1/4 of the resistance you'd get if all the heat originated from the center.
1/4, just by spreading the heat generation out.
Yeah, it makes a huge difference in keeping that peak temperature down, spreading the load, essentially. It fundamentally changes how you might design something to avoid hotspots.
That's a fantastic nugget. But often, the biggest thermal challenge isn't the resistance within a material, right? It's at the joins, the interfaces.
Oh, absolutely. What engineers call thermal contact resistance, one or out voller. This is often the dominant resistance in an assembly.
Why does it happen? I mean, if you bolt two flat metal plates together, shouldn't heat flow easily?
You'd think so, but flat at our scale isn't flat at the microscopic scale. Every surface, even polished ones, has tiny peaks and valleys, asperities.
Like microscopic mountains.
Exactly. So when you press two surfaces together, they only touch at the tips of the highest peaks. The actual solid-to-solid contact area might only be like 1 or 2% of the apparent area you see.
Whoa, really? That little?
Yep. So heat has two main paths. Direct conduction through those few tiny solid spots, which is usually efficient but limited in area.
Okay.
And conduction across the gas, usually air, trapped in the gaps between the peaks. And gases are generally poor conductors.
So the gap is the main barrier.
It's a huge barrier. And modeling the overall heat transfer across that interface, the contact conductance P, is really complex. Equation 1.9 gives a sense of it.
Let's see. It depends on the material conductivity of SICAL, but also surface properties like microhardness setters, the clamping pressure to belt.
Right, more pressure squashes the peaks, increasing contact area. But it also depends on the gas in the gap, its conductivity kilolars, and even its mean free path, lambda.
The mean free path, that's a molecular gas property.
It is. It shows how microscopic physics affects the macroscopic heat transfer, especially if the gap is very small or the pressure very low. It's a fascinating mix of mechanics, materials science, and heat transfer.
Okay, so interfaces are critical. Now, shifting back to fluids in motion convection, how do we quantify heat transfer to a moving fluid, say, inside a pipe or channel?
The workhorse equation there is Newton's law of cooling. QQ equals HS TS TS on a lay.
Equation $1.12.
Q equals HS delta T, where Q is the heat rate, S is the surface area, delta T is the temperature difference between the surface and the bulk fluid, and lower. Dollars is the convective heat transfer coefficient. And finding a dollars, well, that's often the main goal in convective heat transfer analysis. It wraps up all the complexity of the fluid flow and thermal conditions into one number.
But dollars isn't just a constant, is it? Especially inside a duct.
No, definitely not. Particularly in the entrance region. When fluid first enters a pipe, say from a large reservoir, its velocity profile is usually uniform. As it flows down the pipe, viscosity acts, the layers near the wall slow down, and a boundary layer grows until the velocity profile becomes stable or fully developed.
Okay, the velocity profile develops, represented by $6.
And the same thing happens with temperature. If the pipe wall is heated, a thermal boundary layer grows from the wall into the fluid. The temperature profile also develops over a thermal entrance length, $6.
So both velocity and temperature profiles are changing near the entrance.
Correct. And because the dollar depends critically on the shape of those profiles, especially the gradients right at the wall, a dollar changes significantly along the entrance length. It's usually very high right at the start and decreases as the flow develops.
Until both profiles become fully developed, meaning their shape stops changing. Far downstream, the dollar often settles down to a constant asymptotic value for a given flow regime and boundary condition.
Like the example given for a laminar flow in a round tube with uniform wall heat flux.
Exactly. That's a classic case. Once the flow is fully developed, the dimensionless form of Lawler's called the Nusselt number, nulli, becomes constant. For that specific case, nu equals 4.364.
Nu equals 4.364. A fixed number.
A fixed number. Doesn't matter if it's water or oil or air, as long as it's laminar. Doesn't matter if the pipe is tiny or huge. That dimensionless group captures the physics. It's incredibly powerful for designers.
That is powerful. Okay, one last practical application area mentioned, geometric optimization. How do we find the best shape or size for heat transfer components?
Right, specifically looking at forced convection, like blowing air through a heat sink with parallel fins or plates. Often you have a fixed pressure drop available from your fan, delta P1, and maybe a fixed total volume for the heat sink.
Okay, constrained design. The question is, what's the optimal spacing, D effect, between those plates or fins to maximize heat removal?
How do you figure that out?
The insight is that the best performance happens when you size the channels just right, so the thermal boundary layers growing from opposite walls just meet or merge right as the fluid is about to exit the channel length, L.
Ah, so you use the full channel volume for heat transfer without choking the flow too much.
Exactly. Make the channels too wide, and the core flow doesn't get heated effectively. Make them too narrow, and the friction skyrockets for the same flow rate, or your flow rate drops for the fixed pressure drop.
So there's an optimum. And the sources link this to something called the Bijan number.
Yes, the Bijan number, Bijan dollar, is a dimensionless group representing the imposed pressure difference. It's defined as Bijan elbow delta PL2 mu alpha, where mu is viscosity and alpha is thermal diffusivity.
Delta PL squared over mu alpha.
Okay. And there are correlations linking this Bijan number to the optimal geometry. For parallel plates, equation 5.47 gives Bijan profit approx 2.7 tex 14.
D dopped over L is about 2.7 times B to the power of minus 1/4. So the available pressure drop directly tells you the best aspect ratio for your channels.
That's the power of it. It connects an operational constraint, delta P2, directly to a physical design dimension, down dimensional analysis, and optimization theory.
Wow. Okay, what a journey we've taken then. We started way back with the abstract math of vector fields, gradients, divergence, curl.
The basic language.
Use that language to write down the fundamental laws of conservation of mass and momentum, leading to things like the continuity and Navier-Stokes equations.
The core physics in differential form.
And then we saw how these underlying principles manifest in really practical engineering problems, calculating peak temperatures with internal generation, the nightmare of thermal contact resistance, finding heat transfer coefficients, and even optimizing the physical shape of channels using the Bijan number.
It really shows the connection, doesn't it? From the most abstract math to the most concrete design decisions.
It absolutely does.
Yeah.
And it highlights something crucial you touched on. When those full differential equations, like Navier-Stokes, are just too beastly to solve analytically,
Which they often are.
engineers have another powerful tool, dimensional analysis.
Exactly. The sources mention the Buckingham pi theorem. It's a systematic way to take all the variables in a complex problem and group them into a smaller set of dimensionless numbers.
Like the Nusselt number we saw, or Reynolds number, Prandtl number.
Precisely. These dimensionless groups capture the essential physics and ratios governing the system. By focusing on these groups, we can design smarter experiments, develop empirical correlations, like that one new 4.3644 or the Bijan number correlation, and get reliable engineering answers even when a full analytical solution is out of reach. It's a cornerstone of practical fluid mechanics and heat transfer.
A pathway to solutions when the pure math hits a wall. A fantastic takeaway.
Indeed.
Until the next equation design junkies, we are mechanical engineering made simple.